Hello everyone. So here today we are going to talk about a new graph problem, graph algorithm, single source shortest path algorithm. And here we are going to find the single source shortest path in a directed weighted graph. So let's see the problem. Problem definition: the input is a graph, and this graph will be directed and weighted graph. Okay, means each of the edge has a direction and each of the edge has an associated cost, associated weight. Okay, and there will be single source, single distinguished vertex S. So from this S we are going to find the shortest weighted path from S to every other vertex in the G. For example, in this example you can see that this one is a directed and weighted graph. Okay, so in this graph if we go from S to U, all right, S to U, actually to reach from one node to another node there could be multiple paths. So for example, we can go from S to U, like from S to U there is a directed path. Okay, I think this is only one path in this graph. But from S to V we can go from S to U to V. Okay, S to U to V, or we have a direct edge from S to V. Now looks like if we go from if we take this path S to U to V, the cost is 1 plus 2 3. Okay, but if we take the direct path S to V, the cost is 6. All right, so in that case, instead of taking the direct path, we may want to take the path from S to U to V. Okay, so we want to calculate the shortest weighted path. Okay, so based on the weight of each edge we want to find the shortest weighted path from S to every other vertex. All right, so from S to Q, looks like we have a path from S to P to Q. Okay, in that case the cost would be 7. There is another path S to U to V to Q. Okay, in that case the cost would be 1 plus 2 3 plus 1 4. Okay, so in that case we are going to take the path from S to U to V to Q. Okay, so in this problem, in a single source shortest path problem, given a directed weighted graph, and we are going to consider one distinguished vertex S. Okay, so from this single source we are going to find the shortest weighted path from S to every other vertex. Okay, now the naive approach could be like find out every path and then calculate the cost and take the take the path with the minimum cost. For example, take S to calculate all path from S to U. Okay, calculate all paths from S to V. All right, then consider the cost of every path. Okay, then take the path with minimum cost. But this is a very naive approach. All right, so this is a very naive approach. So but in that case actually we have to consider every possible path. All right, and there could be in a directed weighted graph there could be actually many ways to reach from one node to another node. All right, so in that case this is a very expensive algorithm. So but we want to find a more efficient algorithm than this. Okay, so there is an greedy algorithm known as Dijkstra algorithm. So the Dijkstra algorithm is a greedy algorithm. So a greedy algorithm means a greedy algorithm generally solves a problem in stages by doing what appears to be the best thing at each stage. All right, so let's say I am at stage I. Okay, in the having in this stage, all right, I am going to consider what would be best from this stage. All right, so the greedy algorithm approaches from stage to stage. So the last approach we talked about, the naive approach, we talked about considering every approach, I mean considering every possible path and then take the minimum. Okay, and then take the path with the minimum cost. All right, so this is not this is actually considering every possible path, but a greedy approach means we are not going to consider every approach, every possible path. What actually we are going to do, let's see the greedy approach actually generally how it works. Let's see, I am having at one stage. Okay, by having in one stage I am going to consider, I am going to actually consider what appears to be the best thing at from this stage. Okay, so let's see this algorithm. Let's see this algorithm. This is one classic algorithm of classic example of greedy algorithm. Okay, and we're going to see how a Dijkstra algorithm is going to find out the single source shortest path in a directed weighted graph. All right, so this is the graph we are going to consider. All right, and the single source shortest path, the single source we are going to consider from v1. Okay, so we have this graph G, and we are going to consider v1 as a single source node. All right, and we are going to find out the shortest path for every other node in this graph from v1. All right, all right, so before we talk about this example, I want to talk about this Dijkstra algorithm with few simple graph. Okay, let's see, we have a node S, U and V, and this is our source node. So from this node I want to consider the shortest path from every other node. So now let's say I am in node S. So from node S I want to see where I can go and how I can reach to every other node in using the shortest path. So every edge has a cost. Okay, now when I am at node S, what I can see, I can see that I only can reach from S to U. Okay, now S to V I don't have any direct edge. All right, but obviously I can reach from S to V, but I have to take U first then V. Okay, so as I said, in the greedy algorithm approaches stage by stage. Okay, so here what I'm going to do, when I'm at S, I'm at node S, I can see that I can reach U using a direct edge. So let's use another node, and this is 5. Okay, so what I'm going to do, so when I am node in S, when I'm at a node, I can see that I can reach at U using the direct edge, and the distance will be 2. Okay, I can reach from S to P. All right, and the distance or the Q, a cost, okay, or the cost or the distance value will be the weight of the edge 5. Okay, so I am reaching from S to U with distance 2. I am reaching from S to P with distance 5. Okay, now what about V? So from S I cannot direct, there is no direct edge, means I cannot directly reach from S to V. So at this point the distance value will be infinite, means I do not know the distance. So let's reach from S to U. When I will at U, from U I can actually explore other path also. Let's add another node. Okay, from U I can reach to any other path. From U I can reach to V. Okay, so when I will add V, then I will calculate the distance from U to V and U to X, and also this is going to calculate the distance from S to V and S to X. For example, when I will reach from S to V, the distance will be distance of U plus the cost of this edge or the weight of this edge 3. So the distance here will be 2 plus 3, 5. Okay. Alright. So here what happens? 5. So 5 means actually to reach from S to V the cost is 5. If I take the path from S to U and U to V, the cost will be 5. Okay. Now here in this problem I have to find the path with the minimum cost. Okay. So at every stage, if I find a path that is less than the previous cost, if I find a path with a cost which is less than the previous cost, okay, previous distance, then I will choose this path. Okay. So initially when I'm at S, this distance value is infinite because I don't have any direct edge from S to V. Okay. But let's go from S to U. Now from U I can reach to V. Now if I go from U to V, the path will be, the distance will be 2 plus 3. Okay, it will be 5. Then I am going to check whether 5 is less than the current cost. Okay, current cost or current distance value. Okay, now current distance value, the present distance value is infinite. I am going to check if 5 is less than infinite. Okay, if the new distance value is less than the current distance value, if this is less than the current distance value, that means I am going to choose this path for now. Okay, this may again updated, okay, if I take a different path, but for this at any point if I find a path which is less than the current path, I am going to choose this path. Okay. So if I take S to U and U to V, the distance will be 5 and 5 is less than infinite. Then I am going to update the distance to 5. Okay, S to U and U to V. Okay. Alright. Now let's just update few of this value, 3 plus 1 and 1. Okay. Alright, in that case this will be 3. Now S to P, it has a direct edge, so it will be 3. Okay. Now let's see when I am at P. Alright. When I am at P, I can also, from P, I can also reach V. Okay. When I am at P, I can also reach V. Now if I reach V from P, the distance will be 3 plus 1, 4. Okay. So if the new distance is greater than the current distance, means I don't have to do anything. Okay, I'm not going to take this path, I'm not going to do anything. But if the new distance, if the new path has a distance which is less than the current distance, okay, 4, if it is less than the current distance, then I'm going to actually update this. Alright, and that means actually I am going to take this path, S to P, P to V. Okay. Alright, so the Dijkstra algorithm works like this. What I am going to do at every stages, okay, at every stages I am going to take a new path. Okay, and I'm going to compare this the distance of the new path with the current distance. If the new path distance is less than the current distance, then I'm going to update it. Otherwise we are not going to update it. Okay, we are not going to do anything. So let's see actually solve this problem, and I'm sure it will make it more clear. Okay, so I'm going to just erase all of them. All right. All right. So V is my single source. V1 is my single source. Okay. So initially For every initially considering, I'm not going to consider which node has a direct edge or which node doesn't have. Initially, I'm going to initialize every node has a distance with infinite. Okay, all right, and every node has a visited false. All right, so few of the information I'm going to consider. So each node and v6 and v7. Okay, so they are the node. All right, so if node has a visited information, initially each node only the v1 is true, and the v1 will have the distance value from v, okay, 0. From v1 to v1 the distance is 0. Okay, and I'm going to use a previous node from where I am reaching to this node. Okay, so this one, for v1 the distance is 0, previous node is 0, and visited is true. All right, but for every other node the visited is false. Initially I'm initializing, visited is false, and distance is infinite. All right, and previous node is 0 for every other node. All right, so the previous node is going to help us to find a path. All right, which path I am taking to find the shortest distance. All right, so now what we are going to do, v1 has some direct edge to some node. Okay, for example v2 and v4. All right, v2 and v4. So v2 and v4, so the direct edge the v1 has, I'm going to update them. So v2 will have the distance value 2, and v4 will have the distance value same as the weight of the edge, it will have 1. Okay, and every other node will have the distance value infinite, and infinite. So I'm going to actually update the distance value for v2 2, and for v4 1. Okay, all right, so now looks like if I go to v1 to v2 the distance will be 2. If I go to v1 to v4 the distance will be 1. Okay, then what I'm going to do, I'm going to actually choose another node that has the minimum cost. Okay, that has the minimum distance value, so what actually I am doing, intuitively what I am going to do, so if I go to v1 to v2 the distance is 2. If I go to v1 to v4 the distance is 1. So let's just go to v1 to v4 instead of going v1 to v2. So if I take this path the distance is less than this one, and if I take this path, and from this, if I take this node, if I go to this node, and I'm going to consider which node in which node I can reach from v4. So intuitively this may cost less than choosing this one. Okay, so that's why I have the known distance value for v2 and v4, and I'm going to actually choose the node that has the lowest distance value at any point. Okay, at any point, and which has the visited false. Okay, so I know that distance value and they are not visited yet. I have not reached to any other node yet. Okay, but I know that I can go to v1 to v2 with distance 2 and v1 to v4 with distance 1. So what I am going to do, I am going to take the node and that has the minimum, that has the lowest cost, lowest distance. Okay, then I will explore where else I can go. Intuitively we are thinking that this may cost actually much less if I take any other node. Okay, so I am going to actually choose v4 and I'm going to make it known true. Okay, so by known true means I know that I can go to v1 to v4 with distance 1. Okay, now when I'm at v4, okay, when I'm at v4, I'm going to check where else I can go. From v4 I can using the direct edge. Okay, from v4 I can go to v5. Okay, so if I go to v5, what will be the cost? 1 plus 2, 3. Okay, and I'm going to check that whether 3 is less than the current distance. Okay, the current distance is infinite, so if 3 is less than the current distance, I'm going to update it, otherwise I will not do anything. So here if I take this path, okay, the distance will be 3 and 3 is less than infinite. Okay, so I'm going to update it and I'm going to make it 3. Okay, so here actually this is the stage, initial stage. Okay, when v4 is known, this will be like that. Okay, so let's just draw again: v1, v2, v3, v4, v5, v6, v7. Okay, I'll just write down what will be updated. Okay, and here also I have to actually change the value of PV. So when I found v4, v2, the PV will be v1, and for v4 also the previous node will be v1. Okay, now from for v5 I'm going to update the distance of v5. Okay, so for v5 the distance will be still false. Sorry, the known will be visited will be still false. Okay, and the known will the distance will be, I'm going to update this one with 3. Okay, and the previous node will be v4. Okay, now let's see, from v4 I can go to v7, and 1 plus 4, it should be 5. 5 is less than infinite. Okay, 5 is less than infinite. So for v7 I will make it 5, and the previous node will be v4. Okay, from v4 I can go to v6, so it will be 1 plus 8, 9. 9 is less than infinite, so it will be 9. Okay, and it is for v6. For v6 false, it will be 9 and v4. So from v4 I can go to v3. 1 plus 2, 3. It will be 3. It will be 3 and it will be v4. Okay, so looks like these are the node. I can go from v4 to these other node. Okay, so and these, remember, these distance are actually distance from the single source node that we are considering v1. Okay, these are the distance from v1. So from v1 to v7 it takes the distance 5. From v1 to v6 it takes distance 9, v5 3 and v3 3. Okay, every other value will be same as this table, so let's just write it down. v1 is true, v4 is true, and v2 is still false, so it will be 0, 2, 3. v4 is okay, v4 is 1, so 0, v1, v4, v4, v1. Okay, so this is the stage of this graph after v4 is known. Okay, all right, so these are the path actually we have taken. So far these are the path. Okay, v1 to v2. all right, now what actually what I'm going to do, I'm going to choose a node. Now I'm going to choose a node which is false and which has not visited yet and which has the lowest distance value. Okay, So v1 and v4, they are already true, visited, means v1 and v4, we are done with it, we know their distance value. So for the all other node that has the visited value false, and we are going to consider this node, and I'm going to choose the node that has the minimum distance value. Okay, so looks like 2 3 3 9 5, out of this 5 node, v2 has the lowest distance value. Okay, now I'm going to choose v2. Okay, now I'm going to choose v2. So I'm going to make v2 true, and so let's, when v2 is known, I'm going to draw v2 is known or visited. I'm going to draw all the I'm going to actually rewrite the values again. Alright, but I will rewrite only if the value is updated, if the distance value is updated. So let's say if I go to v1 to v2, from v2 where I can go, from v2 I can go to v5. Okay, but if I take this path v1 to v2 to v5, what will be the distance value? The distance will be 2 plus 10. Okay, so v2 to v1 to v2 to v5, the distance will be 2 plus 10, 12. If 12 is less than the current distance, no, right? If I take this path, this is not going to be the shortest path, because the distance will be 12, and 12 is greater than 3. So that means I'm not going to do anything. Okay, so that means I'm not going to do any update in v5. Okay, no update for v5. So from v2 I can go to v4. All right, but v4 is already known, and v4 is already known, and also if you check, like from v1 to v2 2, and v2 to v4 3. 3 is less than 3. 2 plus 3, which is 5. So v1 to v2 to v4, the distance is 5. Okay, and 5 is okay, so 5 is greater than 1. Okay, so 5 is greater than 1, that means I am not going to take this path. Okay, and what happens, from v2 I cannot go to actually any other thing, so that means I don't need any changes in this table. Okay, I don't need any changes in table. Okay, and I'm going to make only v2, the only change will be v2 will be true. Okay, then I'm going to consider all the node that has the false. So it has false 3, v3, v5, v6 and v7. Okay, so you can choose either v3 or v5. All right, so let's choose v5. You can choose any one of them. Okay, let's choose v5. So now we are going to consider where we can go from v5. From v5, let's see, we can go to only v7. Okay, only we can go to v7, but if we go to v7, the distance will be 3 plus 6, 9. Whether 9 is less than 5, no. Okay, if 9 is less than 5, no, that means I don't have to do any changes. All right, I'm not going to take this path. Okay, so here I'm going to make v5 true. Okay, and but no changes necessary for v7. Okay, and from v5 I cannot go to anywhere else, so this will stay same. All right, then I'm going to, I have false for v3, v6 and v7, and the lowest distance as for v3. So let's choose v3 here. For v3, from v3 where I can go to v6 and v1. Okay, but I'm not going to v1. v1 is the single source, so I'm not going to consider this. Okay, so from v3 I am going to I can go to v6, and the distance will be 3 plus 5, 8. Now looks like 8 is less than 9. Okay, if I take this path, the distance value will be less than the current distance. So now I'm going to take this distance and I'm going to update it 8. So when v3 is known, the change will be for v6. Change will be for v6. v6 distance value will be 8 and the previous node will be v3. Okay, all right.